So, welcome everybody. My name is Dr. Matthew Middleton. I'm the director of the Southampton Theory, Astrophysics and Gravity Research Centre, otherwise known as Stag, not to be confused with the bar across the way. If you're expecting to drink a lot, you're in the wrong place. I recently taken over from Professor Kostas Skandaris, who has done an amazing job as director of Stag the last few years, so he's provided a very tough act to follow. Thanks to everybody who has come and everybody online. For those of you who are in here, this is obviously maybe a bit of a culture shock. You know, we haven't been around together in a large group like this for quite some time. Understandably, some people will be anxious, and I completely get that. And so please encourage everybody, just respect each other's space and wear a mask if there's no problem with you doing so. That would be really appreciated. Thank you very much. For those of you who are students, so not senior management, please, you can get the refund on your ticket. The instructions are there, so please do that. There's a few things that we have to do first before we get to the fantastic lecture that I know we're all excited to hear. And so the first thing I'd like to do before we award some prizes is hand over to Professor Robert Wood, who's the Associate Dean for Research in FEPS, and he's going to open the event for us.
A very warm welcome to you all and to the University of Southampton. I'm here representing one of the 5 faculties in Southampton. As I'm here, I'm an engineer, but I'm representing engineering and physical sciences, which is home to P&A and chemistry. And I know that there's a strong collaboration here with maths. So the university is incredibly supportive of fundamental science, and we're really privileged, I think, to have such a prestigious lecture in front of us, but also just to be here in 3D and enjoying what is hopefully a nicer environment than being on Teams or Zoom. So a very warm welcome to this event. I just need to introduce Stag to you all, I think, and it was interesting to me because it reminded me that, so this is the Southampton Theory, Astrophysics and Gravity Research Centre. I hope I got that right, which I think is 3 groups working together as a research centre, and as I say, it spans 2 faculties at Southampton. The mission of Stag Research Centre is to foster and promote cutting-edge research on the fundamental science from the very small to the very big, from the fundamental microscopic building blocks of matter to galaxies, and the universe as a whole. It's quite a big remit. Stag organises several high-profile scientific meetings every year. A recent success is a meeting on the accelerated expansion of our universe, which attracted over 200 participants from all over the globe and featured speakers from Princeton and Chicago universities in the States and many other places, as well as the Stag lecture given by Professor Jim Gates. Another mission is to promote public awareness of fundamental science and to inspire the students of today to become the scientists of tomorrow. Stag also organises an annual public lecture, hence we're here today, given by a highly distinguished researcher, certainly true, today. This explores and explains great achievements in fundamental science. So past speakers were winners of major prizes, including 4 Nobel laureates. So the university welcomes Professor Roger Penrose, who will deliver this year's lecture. I'm just going to hand back to Matt now, as we've got some prizes, I think.
Okay, so every time we run one of these, we hand out some prizes to some of our PhD students. It could be you one day. We have 4 categories. We invite supervisors from the 2 schools to nominate their students, and the categories are best publication in high energy physics, best in gravitation, best in astronomy, and also best contribution to public engagement. So we've split them up. So I'm going to hand back to Robert, see how Smooth that was done.
Okay. So yes, I'm just going to talk about two prizes, and there's another further two to come. So I'm going to be looking at the Astronomy Prize first, and this is awarded to Ed Parkinson for the paper Accretion Disk Winds in Tidal Disruption Events, Ultraviolet Spectral Lines as Orientation Indicators. In this paper, Ed has carried out state-of-the-art ionization and radiative transfer calculations. This work demonstrated outstanding numerical abilities and understanding of physical processes, giving a clear step forward in the modelling of ionization and radiative transfer within accretion disk winds, and shed light on the appearance of complex set of absorption and emission spectral line features observed during tidal disruption events. So, Ed, right, okay, we've got... Right. So the second one is well, in the area of public engagement, and this prize is awarded to Alex Mitchell for his work managing the Particle Physics Theory Accelerate outreach program. In particular, during the COVID-19 pandemic, Alex worked to redevelop Accelerate for online delivery, necessitating a complete transformation away from its usual in-person experiments. Alex has shown great commitment to public engagement throughout his time with us, and he has reached and reaches the end of his PhD. And he reaches the end of his PhD, has ensured that his Accelerate is in a strong position for the future. So, wait, I hadn't realised you're a PhD student, so very well done, Alex, and I don't know where... Yes, okay.
So welcome everyone from the School of Mathematical Sciences. So I'm going to be presenting the next two prizes as the Head of School for Mathematical Sciences, Marika Taylor. So the prize for high energy physics, this is awarded to Davide Bufalini for his original and groundbreaking work, Black Hole Microstates from the World Sheet. So this publication concerns a string theory description of the internal structure of black holes and proves that a certain class of solutions represent the complete set of world sheet configurations. The nomination for this award says that Davide himself came up with the central research question of this paper and that he has displayed academic maturity beyond his career stage, a very impressive work ethic and excellent research skills. So Davide. And our last prize is for gravitation, last but no means least. So this prize is awarded to Fabian Gittings for the paper Modeling Neutron Stars and Relativity, on which he was the lead author. This work concerns the problem of neutron star mountains, which is relevant for the continuing effort to detect continuous gravitational wave signals. It's the first paper which concludes a relativistic description of a deforming force in the model of a neutron star crust, and it gives a very careful description of this kind of force. It's a conceptual breakthrough and is the current state of the art in realistic modeling of neutron star deformations. So congratulations, Fabian.
Thank you so much, Marika and Robert, for handing out those prizes, and also thank you to the prize committee for all the time they spent looking over those nominations. Okay, so we're now getting to the main event, and I promise that I will be quick, because no one's paid £5 to come and see me talk, I think. Am I right? Okay, I'm probably right. Okay. I'm extremely proud to be introducing our speaker today. I suspect if you ask people to list famous physicists, Roger would be fairly close to the top of that list. His contributions over a fantastic career have spanned everything from complex geometry to understanding quantum gravity, understanding the nature of the universe, and of course, black holes. Given his long distinguished career, it's perhaps unsurprising that he's won a whole slew of awards, including the Royal Society Royal Medal and the RAS's Eddington Medal. But I think what most of us secretly desire as scientists is to have something named after us. And I don't mean a street name or a number plate or anything like that. Having a theorem or a discovery named after you is kind of the pinnacle, I think, for a lot of people. And so I tried to find out how many Roger has had named after him. And there's at least 7. Now, I was talking to Roger earlier today, and I've got that wrong. Because he landed a few more on me. I was like, okay, I give up. But just to give you an idea of what we're talking about, there's the Penrose Diagram. So for those of you who are doing physics, you'll be encountering them soon. Penrose Tiling, which is a non-periodic infinite tiling of a plane. A Penrose Triangle. So that's amazing. This is the person for whom a triangle is named after. So he beat out Mr. Equilateral and isosceles. This is big. Penrose Stairs, which were used to great effect by M.C. Escher. He was a phenomenal artist. The Moore Penrose inverse, which will mean something to some of the mathematicians. The Penrose process, which is very dear to my heart because I work on black holes. And the Penrose process explains how energy can be extracted from spinning space-time, which is very cool. And of course, the Penrose Singularity Theorem, which explains that singularities are general phenomena which occur in gravitational collapse regardless of the symmetry of the object that's collapsing. And it was for this that Roger was awarded the Nobel Prize in Physics in 2020. So hopefully that's given you a bit of a taster and impressed upon you how much of an important contribution Roger has made. And I hope that you're as excited as I am to listen to him explain some of these great ideas. So ladies and gentlemen, distinguished guests and colleagues, without further ado, please join me in welcoming the Stag 2021 lecturer, Professor Sir Roger Penrose.
Well, thank you very much for that introduction. It's certainly a great pleasure for me to be back in Southampton. I think the last time I was here, the university was generous enough to give me an honorary degree, so that was some time ago. I hope I can get this thing working, which is questionable, but well, that seems to be the title to my talk, so I guess it's working so far. So I want to talk about space-time singularities and where this takes us. I should start, well, let me start not with this picture, but by talking about, in 1939, there was a paper written by J.R. Oppenheimer well, this was before he started working on the nuclear bomb, but he's known for that primarily. And he and a student of his called Hartland Snyder, they wrote a paper which was considering a rather extreme situation in general relativity, where you have what was called a dust cloud, and this thing was collapsing due to its own gravitational force, and the picture was something which I shall describe to you in just a moment. But the point was that you had this dust material. What dust meant was that the material has no pressure, and it was spherically symmetrical, which meant that the whole thing, as it falls inwards, had nowhere to go except towards the center. So in this solution, which actually is the sort of prototype of collapse to a black hole, but the idea of a black hole wasn't really talked about then, but the fact that you've got a singular state in the middle where the density becomes infinite, the space-time curvatures become infinite, was really not so surprising. I mean, there was no pressure, so nothing to stop the dust collapsing, and everything was aimed towards the center, so the fact that you got an infinite density in the middle was not so surprising. Now, this paper was sitting around since then. In the early 1960s, people started to receive radio signals, which seemed to be extraordinarily surprising to people. These were what became known later as the quasars. These were signals of such intensity that they seemed to be from objects, well, that the mass involved seemed to be more than a galaxy, so, more than a cluster of galaxies, perhaps. So anyway, a very remarkable amount of energy was being produced, but also the intensity of this energy was varied at such a small length of time, in periods of hours to weeks and things like that, which indicated that the body producing this signal must be smaller than the solar system. And something of the mass which seemed to be involved and smaller than the solar system meant that you really had a situation comparable with what the Oppenheimer-Snyder picture was considering. So a collapse past the point of no return. I'll say a bit more about that, which seemed to be, well, it couldn't be exactly like Oppenheimer-Snyder because you're getting signals out of it, which indicated that it was not exactly spherically symmetrical. There was some kind of irregularity involved, and what these signals were doing was puzzling to people. Certainly people were arguing that maybe there was something of this kind of Oppenheimer-Snyder scale. Now let me say a little bit more about the Oppenheimer-Snyder model. This is to get you into the right frame of mind to think in terms of four-dimensional space-time. So what we have here, I don't know if the pointing is going to work. Let me try it. I can barely see it, and maybe you can't. I'm not even going to bother to try and point, I think, because I can't see the dot, and whether you can see it or not doesn't help me, because if I can't see it, I don't know where it's pointing. So let me not use that. But here we have the sort of thing you have to imagine is that at a point in space-time, you've got just three axes to give you the three spatial dimensions, and another axis to give you the time dimension. So you have to imagine that it's 4 dimensions. Of course, in order to picture it, you normally throw away one of the space dimensions. So here you imagine this cone. What is the cone? Well, that represents the speed of light, which is crucial to the whole discussion. And you have to imagine that these pictures are drawn where the speed of light is something not almost infinite, which would be if you had used inches and seconds for your measurements. So you have to consider that if you're using maybe, say, meters for your spatial dimensions, you'll have to think of, perhaps I'm saying it the wrong way around. Suppose you're thinking of seconds for your time dimension, you think of light seconds for your space dimensions. And then your light cones, or null cones, will be something which looks sort of sitting up reasonably. Okay, the yellow thing there is the passage of a photon, if you like, traveling with the speed of light, and the dimensions are chosen so that it's something tipped up at a reasonable angle. Okay, so you have to think of these things as being the fundamental objects, and the axes are irrelevant, and the particular photon trajectory is irrelevant. We're considering mainly the totality through that point, space-time point, or event as it's usually called, all the possible directions of photons. And they're represented by the light cone, as I might call it, or the null cone, technically. At each point, you've got a null cone. Okay, now you have to imagine that your space-time, you have these cones drawn on the space-time. This is the main important structure of space-time, are these null cones. As I say, you've got to imagine a few more dimensions. And it looks as though I've got a two-dimensional surface here. It's got to be four-dimensional, and the cones look as though they're three-dimensional. Well, you've got to imagine they're four-dimensional. But get used to the picture. The main structure is given by these cones all over the place. Now here, I've indicated the Oppenheimer-Snyder collapse. At the bottom of the picture, you must imagine these lines going inwards represent the world lines, if you like, of the dust cloud collapsing inwards, and they fall in, and what happens to the light cones is they start to be sort of pulled in and tipping inwards, and right in the middle you find the singularity, so the matter is concentrating in the center. This is actually the famous Schwarzschild solution of Einstein's equations. Outside the matter would be some other solution, but external to the matter, you have the Schwarzschild solution, which was one of the very earliest solutions to the Einstein equations, and you have to write it in such a way that you can continue beyond what Schwarzschild would have stopped it at the. You see the cylinder in the middle, which represents where the cones tip over and they point inwards, so that if you were trying to follow a time-like trajectory, see, matter has to have its world line within the cone, so they would be guided inwards. This is, in fact, the picture of a collapse to a black hole, but in this very idealized situation, where you're looking at this spherically symmetrical collapse, and that the collapse is of this dust which has no pressure. The actual no pressure, it doesn't make much difference, but the key thing is that you have spherical symmetry, and so it's going nowhere to go except straight in. Okay. Now, this, at the time of this, the quasars were being considered, much later than the paper, of course, that was 1939. So in the early 1960s, people began to worry about this collapse and what would happen. And at the time, I was in Princeton a bit earlier than this. Well, I think during the quasar times I was in Princeton, and I used to have discussions with John Wheeler, who was very intrigued by this whole problem, and the question about the singularities was very much discussed. Now, there was a paper, I can't remember where I was at the time now, whether this was in Princeton or somewhere else, but at the time there was a paper written by two Russians, that was Lifshitz and Khalatnikov, and they had looked at general solutions of Einstein's equations and had come to the conclusion that in the general case, you would not get singularities. So this was the general view. I think people had referred to this paper often. I had a look at the paper. I didn't look at it very carefully. I didn't notice that there was actually a serious mistake in the paper. I think the mistake was noticed later by Belinsky, and but this was after the work that I did on the subject, when the people believed that this paper was correct. I looked at the arguments, and I wasn't very convinced by the arguments in the paper. I could say, okay, maybe, but maybe not. It didn't persuade me necessarily that you would get the situation that they predicted, that there would be no singularity, no sort of infinite curvature, that sort of thing, appearing in a generic collapse. Now, I began wondering about this thing, and I had thought in general terms for some quite different reason. I had a paper in the Royal Society which had to do with looking at what fields, electromagnetic fields or gravitational fields, and radiation, and how that radiation behaved when you went out to infinity. And in order to use the techniques I was using, I needed to see that the structure of infinity had to be like a sphere. So what I mean by that, you see, looking at all the directions around, see, at a point, you see all the possible directions you can see, all the light rays coming into your point will constitute a spherical family of these light rays. But at infinity, it might not be a sphere, it might be something more complicated. And I tried to prove, because it was crucial for the arguments I used in this paper, that it had to be like a sphere. And could it be a torus or some more complicated topology? And I presented an argument in the appendix, which I thought was a complete waste of time, because if you're any normal consideration, you think you might as well assume it's a sphere. Why bother with these complicated calculations? So I developed an argument looking at what futures of regions looked like. And so I began to get a feeling for what futures of regions looked like and what their boundaries looked like. And it was useful to me, so although it may have been a complete waste of time putting this argument in the appendix to the paper, which I did, it was a sketch of an argument, really. I had some familiarity with boundaries of futures. And so I think it was somewhat later than this when, probably in it would have been in 1964, and I remember having a conversation with a colleague of mine, Ivor Robinson, who worked in Dallas, Texas, but he was very, very English, and he spoke. I think Americans all loved him because he had this wonderful way of speaking, it was a wonderful way of speaking. And he was talking to me, I remember, about something or other, I have no idea what. And then we crossed the street. And when we crossed the street, the conversation stopped. And it started again at the other side of the street. And then when he left, I remember having this strange feeling of elation. And I couldn't think why I was feeling this elation. So I went through all the things that had happened to me during the day, what I'd had for breakfast, what happened in the tube coming in, and so on and so forth, until I got to crossing the street. And I realized I must have had this idea crossing the street, which is this idea of a trapped surface. Now this picture here is from the article which I sent in 1964, I think, to Physical Review Letters. It was published in 1965, where I considered the collapse. Now this picture is a bit like the Oppenheimer-Snyder collapse. It's very similar. I'm looking at the spherical symmetrical case, but I was considering what happens when you perturb it. And this little ring in the middle, you have to imagine that there is another dimension, and so that ring, which looks like a ring, is really a sphere, and it has the property that if you had a flash of light on that ring, that the light rays coming from it would, not just the inward light rays, but the outward ones, would both be converging locally. So the key point was that you can have a surface here which is rather, it represents, in a certain sense, the point of no return, which is what's going to give you this collapse situation, and you've gone a little bit too far, and then you can't really retrieve it. It's what I call a trapped surface. And it's trapped because the light rays from it are converging, whether they're, in a sense, outward or inward, they're both converging. And then I looked at the future of this, and so you see this shaded region, and the future of this, and I had enough familiarity what boundaries of futures look like. When I say the future of it, you look at all the points that can be reached by time-like curves, so that means world lines which lie within the cones, and what is the boundary of such a region, and the boundaries of such a region could be pretty complicated. Now I've turned something off by pressing the wrong button. How do I turn it back again on? That's the right button. This is the future of a point. You see, it can look fairly complicated. In the back, you see some complicated stuff going on. This is a better picture of what's going on. You can have light rays which start to cross each other, and it can look really quite complicated in a general situation. How do you say something sensible about what goes on? Well, if you look at the boundary of the future, all this complicated stuff in the middle with the caustics and the cusps and all that stuff is not going to be not bother you, because the boundary of the future stops before you get there. And you can see it's going to cross over because there are things like conjugate points. I'm not even going to talk about those really, but you've got the caustics which are inside and the conjugate points which are inside. And the boundary itself isn't too bad. Although the light rays start to cross each other, each point on that boundary will lie on a null geodesic, or light ray if you like, which you can extend backwards from that point and remain on the boundary. So this was a key thing to know about boundaries of futures, and using that piece of knowledge, now I have to make sure I don't press the wrong button here. Yes, using that piece of knowledge, I was able to show, I didn't particularly want this picture just yet, that you would have necessarily not as nice, simple singularity like this in the middle, which is spherically symmetrical, but something goes wrong. And I used the argument that you trace the light rays on the boundary of the future, and they have to form a region which is compact, and you consider that there is a contradiction with the fact that you can have a non-compact initial surface that's at the bottom. You imagine that you start with an initial surface which goes out to infinity, and then some local region, and that collapses, and you get a contradiction between this compact region in the middle and the initial surface. So this was the basic argument in the proof that I presented. It was quite curious at the time. I wasn't quite expecting the reaction I necessarily got. I remember I was in Princeton somewhat after the publication of this paper, and Bob Dickey, who is a distinguished experimentalist and theorist, and he slapped me on the back and said, "You've done it. You've shown general relativity is wrong." So that was the view of many people. If you get these singularities, this must mean that general relativity is wrong. That wasn't my view of it. It just showed you got singularities, and you have to understand it somehow. Well, I didn't know at the time that if you use Bob Dickey's theory, which I think he was rather hoping that his theory would work better than general relativity, the singularity theorem worked just as well in his theory. So I could have said that to him. It disproves his theory just as well as GR. I didn't know enough about his theory at the time. But anyway, that was, I think, rather the view that a lot of people had, not that black holes were really out there. It doesn't even show you got a black hole. You see, it shows that you get singularities. The Nobel Prize was given for black holes, and some of my colleagues point out that wasn't what I showed, and they're quite right. What I showed was the inevitability of the singularities, and the singularities might be what are called naked. And I sort of believe that could have been the case. It wasn't at all obvious to me that they were necessarily inside black holes. And I played around with the idea that you might get naked singularities. But later and later, I began to be pretty convinced that there had to be black holes. And it's still an unsolved problem, actually, whether you can conceivably, in general cases, get naked singularities. Let me not talk about that. I don't want them to take my Nobel Prize away from me. Anyway, as I say, this is the kind of thing you get. Now, you see, when I gave a talk about this at King's College London. I was very pleased because J.L. Singh was there. He's somebody I had a lot of respect for because he was very geometrical in his way of doing general relativity, and I liked his books especially in general relativity. And I remember being very pleased that he was there at the talk. The person who was not there at the talk, despite what the movie seems to imply, was Stephen Hawking. Now, Stephen Hawking was, although the movie shows him with sparks coming out of his head or something, by being inspired by this lecture, he wasn't actually there. But that it wasn't so bad, because Dennis Sharma, who was a great friend and somebody I learned a lot of physics from, and he was in Cambridge, and he heard about my talk and asked me to give a repeat, which I did do in Cambridge. Stephen was present there. More importantly, he was present at a private talk I gave to Stephen and George Ellis, possibly Brandon Carter, people who were present. Certainly George Ellis was there. And I was able to talk in detail about the arguments I was using. Stephen picked up on these arguments very quickly and started to use them to cosmology. So this is really the other end of the issue. I was talking about singularities in the future, when you have a collapse, and you inevitably get these singularities without violate. The crucial ingredient you needed was that the energy, local energy, never became negative. That meant that light rays which were focusing couldn't get unfocused, basically. And with the positivity of energy, this meant they wouldn't get unfocused. And that was a crucial argument for showing that the future of the trap surface had to be a compact region, sort of closed up region in a sense. Now, you don't have this advantage in cosmology because you normally think of the space as going out to infinity, and you need other arguments. Well, Stephen did have very quickly a use of my actual result in a reverse time direction, which he applied it to cosmology in rather particular circumstance, but it was impressive that he came up with that very quickly. But then he worked on generalizing my techniques, and applying to the Big Bang. So here I have a cartoon of the universe as a whole. The Big Bang is at the bottom. Then we have the expansion. And if you see this, not known at the time, but this accelerated expansion which seems to be taking place. And so it starts to expand exponentially, as far as we can see, which would be an effect of the presence of a positive cosmological constant, which is certainly the way I looked at it when the arguments sort of at the turn of the century that this is what was happening, that the universe is accelerating expansion. In this picture, you may see that it looks as though it's spatially closed, but needn't be, because as you go around to the back, you see it wiggles around and maybe it doesn't close up. So it's not meant to indicate that the universe is spatially closed. It might close up or it might not. You want arguments which will apply in both cases. So Stephen generalized the arguments I was using. I won't indicate much about the generalizations except to use a picture like this. One of the important developments that he introduced was to study what he called Koshi Horizons. See, if you have a surface, the bottom line there is your initial data surface, and you have data on that, and then you see what is the sort of region which could be determined by data on that surface, and is there a boundary to it? So the top pair of lines represents the boundary, and that is what you call, what he termed, christened the Koshi Horizon. And Koshi Horizons have properties very like boundaries of futures, sort of the other way around in time, but very similar to it, and you can prove things about null generators, null lines, null geodesics lying on these boundaries. And it was very important to talk about Koshi Horizons and the domain of dependence, which is the region within it, and you have certain theorems which tell you that the light rays, or the time-like curves to that, say that point, not the one right at the top, but just below that point, you can consider the path of that, and time-like curves into that point, do they have a maximum in the length of those curves, and things like that, which were very important in generalizing these theorems. So Stephen produced a family of papers for the Royal Society, and at the end of this, he and I got together and had a general theorem which encompassed most of what had been done previously. So I'm glad to be involved in this development which Stephen had done, usually developing these arguments in these important ways later on. Okay, now is the universe like this? Now here I have studying what people consider to be the very early universe. There's this thing called inflation. Now, inflation, I think people, before going to talk about inflation, let me really discuss the problem I had with thinking about the Big Bang in relation to the singularities in black holes. I remember having this conversation with James Peebles, who was Nobel Prize winner in physics the year before I got mine, and he was working on the early universe and the very important work that was done into studying what happened in the very early universe. And I remember having, I think there was a car which was about to drive off to a conference I was at Princeton at the time, and the car was driving from Princeton up to Hoboken, which was where there was a conference going on. They had these conferences quite often, where people from New York State and various parts of the state wished to come back to this meeting at Stevens Institute, which was just across the river, and it was Hoboken, New Jersey. And the cars used to drive up there to these conferences. They were very important, and I certainly went to many of them. But since I saw Jim Peebles sitting in the back of the car was full, so I had to go in another car myself. But I thought I'd better ask him. I said, well, look, there are all sorts of other models than the ones that you cosmologists study. So why don't you look at all these other situations instead of spending your whole time looking at these very simple cosmological models where all the symmetry is assumed? Why don't you look at all these other cases? And he looked at me and said, because the universe is not like that. And I thought, my God, it's not, is it? What he meant, I think, was when you look at the microwave background, it is very uniform over the sky, and you don't see a very complicated thing like all these situations that you can have in gravitational collapse. And that was a sort of turning point for me, because I'm back and think, why on earth is the universe that we see, the Big Bang singularity, so different from all these possible kinds of singularities that you get in the future when it can collapse? So this is a very curious thing which puzzled me for a long time. Now, one of the answers to this question, apparently, was that inflation, this thing which is supposed to happen in the early universe, would have ironed out the universe, this very rapid expansion. And here I'm imagining a magnifying glass looking at the Big Bang, and what are you supposed to see according to inflation? You're supposed to see something like this, with this exponential expansion, very much like, in overall terms, the exponential expansion that we are seeing in the microwave. Well, we are seeing in the sense of not the microwave background so much, the supernovae which indicated this exponential expansion, and other observations. So we seem to be seeing an exponential expansion on a much, much different scale, but this would have been way, way, way tucked into the Big Bang within the first 10 to the minus 33 seconds, 1 over a number with 33 decimal places, 33 digits. So a thing like that, a ridiculously tiny fraction of a second, this exponential expansion was supposed to take place, and it was supposed to smooth the universe out. So for some reason, that was supposed to be why the universe was so smooth. I never believed that argument, because why didn't that happen the other way around in the future? So whatever inflation or no inflation, this is the sort of picture. You have anything like a generic collapse. This is now time, as in most of my pictures, time will be going up the picture, and instead of producing a nice little Big Bang, very smooth Big Bang, you get a great horrible mess like this, and this mess will be such that the curvature, I'll say a little bit more about the curvature in a minute, the nature of this curvature, but it's a great mess. So why is this great mess not like what we actually see in the past? And it just seemed to me, because you could have this in the future, even you could start working out the probabilities too, because here we have something which is a congealing of many black holes, and when you start putting in the entropy value for the Wittgenstein-Hawking formula for the entropy, and you see that the entropy in the universe we know now is utterly dominated by the entropy in black holes, completely swamps anything else. And when it starts to collapse, that entropy is going to get worse and worse and worse. And when I say worse, I mean bigger and bigger and bigger. And it's absolutely huge, and it dominates absolutely anything that we can conceive of. And why is the probability, just in terms of probabilities, the fact that we get something like that rather than this is just incredible. So it can't be just chance. Well, people talk about chance, and they talk about the anthropic argument, and most of them don't have people in them, and so on and so on, and that doesn't really work, that argument. You can certainly see it's not nearly good enough to get you down to what's needed here. People think, oh, well, it's only a little tiny part of the universe which expands out by inflation. That argument, you can see it doesn't work by considering the sort of probabilities involved. Nowhere near working. So there must be some other reason why the universe has this very special energy state. I forgot what the next slide is, but let me say it here. Yes, that's good enough. One way of saying what's special about the Big Bang is that the Weyl curvature, which I'll say something about in a minute, is near to being zero. Now, what is the Weyl curvature? I think it's useful to think in terms of electromagnetism. You see, in electromagnetism, or Maxwell theory, this amazing theory that Clerk Maxwell produced, where you have two tensor quantities involved. One is the Maxwell field tensor, that's describing the electromagnetic field, and this was Faraday's considerations were very important in Maxwell's discovery of his equations. So you've got the field, that's the Maxwell field tensor, and you've got the charge current vector. So you've got one thing is the source, that represents the charge, maybe magnetic fields and so. Anyway, the sources, and then you've got the field. Now you see, in general relativity, people don't tend to think of it that way, but it's useful to think of it that way. See, Einstein's equations tell you that this thing called the Ricci curvature describes the matter mass energy distribution, and that is the source of the curvature. So that is the Ricci part, and that, the way I'm thinking of it, if you imagine at the top somebody gets a vertex of somebody looking back along the past light cone and seeing what the light rays do, the inward focusing is due to the Ricci tensor, and the rest of it is the distortion due to the Weil tensor. So we're thinking of the Weil curvature as the analog of the Maxwell field tensor, and the Ricci tensor as being the analog of the charge current vector. There's a sort of difference here that they're same order of differentiability, and we'll never worry about that because that's not the thing to worry about anyway. So let's not go into that. But you have this nice splitting of the curvature in these two parts. And for some reason, it's not the way people tend to think about it, but I think it is a very useful way of thinking about it. And the Weil curvature you can think of rather nicely here. This was, if you imagine looking at the sun, well, don't do it unless there's an eclipse of the sun, but that was what people did, to see the first effect of the Einstein theory, to see the bending of light due to the sun, and light rays coming through the sun, if they could get through, which they don't, of course, but you could think of the light rays getting through, that would be focused, so as a magnification effect. And that magnification effect would push the field of vision outwards, and that's what it does to the star images. And as an image gets pushed outwards, well, it gets pushed outwards less and less as you go out, so you see that, and also it's stretched outwards because the transverse direction gets stretched outwards, so that a little circular pattern gets deformed into an elliptical pattern. So that's the main point I'm making. This is directly the effect of Weil curvature, is the distortion of the field of vision where the circular shape gets distorted into an elliptical shape. And so that is the effect of Weil curvature. So I really want to talk about these two kinds of curvature because that's the main point of the argument. Okay, now let's talk about, I'm going to talk about entropy of, first of all, let's say a gas in a box or some simple ordinary stuff. And in the top three pictures, I'm thinking about a gas in a box. And time is now moving horizontally from left to right, so that's the picture we're thinking of. And you start off in this picture with the gas being constrained to being within a little box, then you open the box, and the box spreads out through the box. The gas spreads out through the box. So this is a general feature of normal matter, that as the time increases and as the entropy increases, so entropy is increasing with time increasing, so that's in accordance with the second law of thermodynamics, the gas becomes more and more uniform. So this is a general trend, that for entropy increasing, you get uniformity increasing. But the bottom three pictures are representing now a galactic scale box, so an absolutely enormous box with lots of stars in it, and these stars are interacting with each other gravitationally, and so they clump. They start clumping and clumping until they get to black holes, where the clumping is an extreme situation. And so you're seeing something which, as time increases from left to right, the entropy is increasing in the same way as entropy is increasing in the top picture, but the uniformity is decreasing. So the key thing is that as the entropy increases, with most matter, it gets more and more uniform, whereas with gravitating bodies, it gets more and more ununiform or more and more clumpy. So that's the picture. And this is even more, you see, I kept worrying about this. As you imagine going back and back in time to the earliest thing that people see directly, in other words, the microwave background, this radiation coming to us from, well, 380,000 years after the Big Bang. That's the first time when light actually starts to escape. And when I say light, it's the microwave. It can actually get out, and so you have evidence of it. The earliest observation from a satellite, this is the Kobe satellite, and it looks at this microwave background, and it sees this curve. Now this curve is the Planck, the continuous line is the Planck curve, which would say what maximum entropy would be like. The horizontal axis is that's the frequency, and the vertical axis is the intensity. And this is what Max Planck shows, that you get this particular curve for, it's the beginning of quantum mechanics, to show that you explain this curve, and you have to have the fact that you have particle nature of matter as well as the wave nature. But you see this very beautiful curve. Now, what are these vertical bars? Those are the error bars, but you have to bear in mind that these error bars are magnified by a factor of 500. So if you squash them down to what they really should be, even the worst ones at the right, they're way within the thickness of the incline. So you have a very, very perfect Planck spectrum. So what this tells you is you go back and back and back in time, and the entropy should be going down and down and down as you go back, according to the second law. It goes down and down and down until you reach a maximum. A maximum? A maximum. Because you're seeing this curve. Well, that's true. What you're seeing is the maximum in the entropy if you're talking about matter. But if you're talking about gravity, so going back to my previous picture, it's what you're seeing. Well, you see, consistent with the top picture, yes, indeed, you're looking at maximum entropy. But the thing which is low in entropy is in gravity. Now, the gravitational degrees of freedom are described by the Weyl curvature. So what you seem to be seeing, and this is just sort of an observational fact, that what you seem to see is that the Weyl curvature in the Big Bang is very, very small. The gravitational degrees of freedom have not been activated in the very beginning. For some reason, they were suppressed. So this is a huge puzzle. I began to think about this puzzle, I think, in terms of, you see, people used to say, well, you get these singularities, but that's classical general relativity. And that's, you should be starting to think about quantum gravity. Yeah, okay, well, I agree with that. When the curvatures get so enormously large, that means the radius of curvature gets enormously small. What does enormously small mean? Well, the Planck scale would be, that's when things really you have to think about quantum mechanics, so the argument goes. You're looking at something like 20 orders of magnitude smaller, say in the radius of a proton or something like that. So 10 to the minus 33 centimeters, something like that. Okay, well, that will happen. You get these curvatures go up and up and up, and then you get quantum gravity. So the argument is, well, to understand these things, you've got to do quantum gravity. But then, how do you get this enormously strange disparity between the future and the past? Well, my view was, okay, maybe it's quantum gravity, okay, quantum gravity, but it's a pretty damn peculiar kind of quantum gravity. But this seems to me maybe not so unreasonable, because the view I was having about quantum gravity is that it is not like other theories. You see, people were saying, oh, well, you quantize gravity. That's what you're supposed to do. You use the rules of quantum mechanics to change gravitational theory. But my view on this for quite a long time was that that can't be the whole answer. And what I've shown you here is the basic principle of quantum mechanics, if you like, is principle of superposition. If you can have a thing being here or a thing being here, sort out if it's an atom or something, then it can be here and here at the same time. So you have this superposition of states. If that could be a state in quantum mechanics and that can be a state, then you can have all these combinations where it's there and there at the same time. That's a very basic principle of quantum mechanics. So that's the principle of quantum superposition. What's the basic principle of general relativity? The principle of equivalence. So that's what I'm showing here, and I'm imagining, well, Galileo, he could be, I don't think he actually dropped clocks. People tell me he never actually did it, but who knows? He might have done it, or he might have imagined it, but he certainly imagined it, and he certainly knew that the air resistance would give you, if you dropped a feather, it would float, but that's due to air resistance. He was well aware of that. If you imagine dropping things without the air resistance, a big rock and a little rock would fall together, and we imagine here a little insect on the big rock looking at the little rock, and it's as though for that period of it dropping, there is no gravity. Gravity is something you can remove by falling freely with it. It always struck me there's a huge irony here, because when Newton wrote his Principia, he started off thinking about gravity, and that's the archetypal force. And he's also considered all sorts of other kinds of forces. And of course, that was very important to the development of physics. You consider nuclear forces, all sorts of forces other than gravity are now very much part of physics. The one exception is the one which started the whole thing off. In other words, gravity. Gravity is the only force that you can get rid of by freely falling with it. And bottom, I have this, well, sort of 2001 type of space station, and the astronaut not noticing the gravitational field of the Earth because that astronaut is falling freely in the gravitational field of Earth, in other words, freely in orbit. So that you can get rid of it locally. But you really need Einstein's theory to get rid of it all over the place. Locally, of course, isn't the whole answer. But what happens when you combine the two together? I won't go into this because it's an argument which needs more discussion, but I did consider this problem of trying to do quantum mechanics with the principle of equivalence. So what I'm considering here, you're doing a tabletop experiment, and you are trying to take into consideration the Earth's gravitational field. Well, the way that most physicists, sensible physicists, would do this, they put what's called putting a term in the Hamiltonian, which takes into account the potential for the Earth's gravitational field, and you just chug away doing ordinary quantum mechanics. And that's what the green coordinates, I think, are doing. I haven't got it the right way around. That's the little letters, I think that's the green ones. Or you could do it Einstein's way. You say, no. You don't put the gravitational field in because it's not really there. You freely fall, and you use coordinates which freely fall, and you do it all over again, and there is no gravitational field. You just use coordinates which freely fall. Two ways of doing the same thing. What happens? Rather surprisingly, what happens is it doesn't make much difference. That is to say, you've got the green one or the purple one, and one of them is the Einsteinian one, and the other is the Newtonian one, if you like. I call it the Einstein perspective. That is, say there's no gravitational field, you can get rid of it by freely falling, and the Newtonian ones, it's a force there. The difference is a phase factor. That's each of the thingamajiggle in the middle there. And what's the phase factor? Well, if you know your quantum mechanics, and you say, who cares? Because you're going to when you make your measurements, you just cancel out the phase factor. But if you're looking a little more carefully at that phase factor, you see there's a little awkward little term, which is t cubed in the exponential. And if you're really careful about what you're doing, you say, actually, it's what's called a different vacuum. You again say, who cares? Stick to your vacuum, and it doesn't make a difference. Strictly speaking, that's almost true. But what's not true is it works if you have a slightly different problem, really when it's slightly different, but importantly different, is that in the part of your experiment at the top, it's not really just the Earth's gravitational field you're considering, but maybe some lump of material, and its gravitational field is part of the experiment. So I'm considering that you're really worrying about its gravitational field and not to the Earth's gravitational field. The Earth's one cancels out, that's true. But its gravitational field causes you a real problem because you've got different vacua and you have to cheat. I don't have any way of doing this without cheating. So what you can do is to cheat and take into consideration of how bad your cheating is, and you do a little bit of integration by parts and that sort of stuff, and you come out with a thing which says, okay, there is a certain uncertainty in the energy of the system. And so what I then do is say, okay, there is this energy in the uncertainty of the system. Then I use the Heisenberg time energy uncertainty, and I say that this superposition of this body in location of two positions, that thing has an energy uncertainty, and this means that superposition has a lifetime in accordance with the Heisenberg time energy uncertainty. Well, there's a bit of a flapping of the hands in that argument, but nevertheless, that is the argument, and you come up with a formula due to Dioschi. He'd done this differently from me, somewhat earlier than I did, without perhaps the justification that I had, but it comes up with the same argument for how long a superposition will last. And it's a very intriguing and important problem, because it's the question, you see, quantum mechanics is this fundamental problem with it, and there are so many different viewpoints that I won't even begin to talk about them. The problem is what's called the measurement problem. And the measurement problem has to do with the fact that, see, quantum mechanics people say, well, nobody understands it. There's good reason for not understanding it, because it's inconsistent with itself. They don't usually say it so brutally as that. But the inconsistency is that there's this wonderful equation which tells you how the quantum state evolves. That's called the Schrodinger equation. And this equation tells you how the state evolves. However, then you make a measurement, whatever that means, and when you've made the measurement, you don't follow the Schrodinger equation, you collapse the wave function. Schrodinger was very upset by this, quite correctly, and he produced this theoretical example of his cat in a box, which was in the superposition of being dead and alive and all. This was a demonstration to show how absurd his own equation was, basically. And it shows that you have this completely absurd situation. The world does not follow his own equation. Seemingly, it seems to collapse from time to time. And what determines that collapse? Well, the view I held for a long time is that it's gravity. And maybe there are experiments which will test to see whether this is this formula the correct formula for telling you whether a superposition will collapse or not. Well, there are certain experiments. There's an experiment that Dirk Baumeister had been trying to perform for many decades now, I don't know how long, still hasn't got an answer. There are experiments being proposed. One of these experiments is due to Lisette Winters-Gurdy, who's right here, and I hope she will be able to perform this experiment and see whether it's in accordance. That's to say, you see, put a Bose-Einstein condensate into a superposition of two locations. Does it go into one or the other, or does it, after the lifetime you might expect it to have, go to a superposition, stay in a superposition, or does it go to one? Very important. I think it's one of the most important, I think the most important thing to decide in physics. We don't know the answer to this. Does it follow the sort of thing that we say here, or what? But I have to go back to what I'm talking about, which is cosmology. And does it, you see, I got stuck with this because I couldn't see why anything related to this question. I mean, why do we get this huge difference between the singularities of collapse? Is it quantum gravity? Do we have to change our theory of quantum gravity to accommodate and produce this huge difference in the singularity structure, or what? I don't know the answer to that, but what I do know is there is another way of looking at this whole problem which is much more fruitful. And this other way of looking at it is illustrated by this Escher picture. This is one of his famous circle limits, and these circle limits are describing a kind of geometry known as hyperbolic geometry. I'm not going to worry about what that geometry is, but he illustrates it very beautifully in this picture. It's the Beltrami disk. It's usually referred to as the Poincaré disk, but Beltrami did it much before Poincaré, so I suppose we better call it the Beltrami disk. And this is a picture of hyperbolic geometry, where these fish creatures, well, they are represented conformally correctly. Conformally means that angles are correctly represented. And in this picture, the circles, you see, this was the first of the circle limits, and the fish creatures have eyes which are exact circles. And this is rather handy because the circles are exact circles right out to the edge. I've seen the original of this picture, and it's remarkably accurate, right to the edge. It's how he was able to do this, I find really extraordinary. But anyway, it's remarkably accurate. And I think he learnt about this geometry from Coxeter. He was certainly able to illustrate it in this remarkable way. So the infinity of this world of these fish, we from the outside can look at it if we respect the conformal geometry of this picture, so the angles are right, the angles of the fish's wings or fins or whatever you call them are the same right to the edge, their eyes remain circles right to the edge. So the fact that they're smaller is not the important thing. If they don't know big from small, and they think the edge is infinity, but we from our perspective can look at infinity as a nice boundary. So it's a point of view which I've played with for a long time. And when we go back to the light cones, because you see I was talking about the space-time geometry, there is, if we just talk about the null cones, this is almost all the local geometry. When I say almost, what do I mean? The metric of space-time is determined by 10 numbers per point, and 9 of them are the light cones, or the null cones. When I say 9 of them, I really mean the 9 independent ratios of those 10 quantities. So that the null cone is almost all the structure. It's just one more component you need. What is that one more component? That's a scale. What is that scale? Well, it's how clocks behave, if you like. And clocks are determined because of these two most famous formulae of 20th century physics. What are they? E equals mc squared, that's Einstein. E equals h nu, that's Planck. Nu is a frequency. Put the two together, they tell you that frequency and mass are equivalent. So a massive stable particle is a very, very perfect clock. And the piece of information that you need to give you the metric geometry of Einstein, as opposed to the conformal geometry that Escher was just illustrating, is the thing which is determined by mass. In other words, the scale. So that is the key point. And the other side of that argument is if you don't have mass, you don't know the scale. So this is the important thing I want to make. What happens when you don't have mass? Well, let me move on to well, this is if you don't have mass. Then you think about the light rays, they don't even hit these surfaces. So going back to my previous picture, a time-like line, the blue line, these are two clocks, and they hit these different surfaces, which sort of tick number 1, tick number 2, and that gives you a feeling for how clocks behave in relativity. Okay, we don't need much of that because I'm going to think about light rays. They don't hit any of these surfaces. They just need to know the cones. It's even more than that. The wonderful equations of Maxwell, which I described, if you talk about the Maxwell, free field Maxwell equations, they don't need to know the curve, they don't need to know the scale at all. They just need to know the conformal structure. In fact, you can change the scale from here and here all over the place. It can be different all over the place. The Maxwell equations are completely insensitive to that. They just know the cones. That's all they need to know. That's a characteristic feature of massless things. They don't seem to know anything apart from the cones. The story's a little more complicated than that, and let's not worry about it. So that's all we need, is the cones. Okay, space-time. Now I'm thinking about the future infinity because of the discovery of the exponential expansion, or maybe the cosmological constant being positive. You have a space-like infinity. So the future infinity is like a sort of time. It's time infinity, if you like, but it cuts across the space-time picture horizontally in a sense. It is like a moment of time. And that's a feature of having a positive cosmological constant. Now, this picture is drawn so that you can imagine the future being squashed down to be a finite region, but also the Big Bang to be stretched out. Now, I'm using here an idea which was really due to my former student, Paul Todd, who, rather than saying I used to go around saying, well, let's say the Weyl curvature hypothesis, the Big Bang, for some reason we don't know, had to be zero. His way of looking at it was much more productive than my way of thinking about it, which is to say, okay, let's say it's conformally extendable. It doesn't mean the Weyl curvature is zero, but it has to be finite. So let's suppose, not that the Weyl curvature has to be zero, but the condition on the Big Bang to see, for whatever reason it might be, is that it's still conformally extendable. So you can stretch it out to make a nice, smooth boundary. Now, there's nothing wrong with this picture. There's nothing outrageous about this picture. Maybe it's smooth at both ends. I began to think about this and thinking about, it's not just all that, well, let me go to the next picture. This is not outrageous, I say. That's, you might not believe it, but it's not outrageous. However, the next picture is outrageous. This is the picture I want you to take seriously. Taking it seriously is about outrageous, a bit outrageous. You might say, what am I doing here? Well, I'm matching the remote future of a previous, you see, our eon is the one in the middle there, let's say. There was, when I say eon, I mean Big Bang to remote future. That's what I mean by eon. Now, there was a previous eon, I say, its Big Bang to its remote future. Its remote future was the conformal predecessor, if you like, of our Big Bang. So its conformal structure fitted on to the conformal structure of our Big Bang. Does this make geometrical sense? Well, it seems to. Does it make physical sense? Or is it outrageous? Well, it's not too bad as it looks, because you see, when you conformally squash, that means you're making distances smaller. There's the, what do you call it? The thing which goes along with it. There's a term which has gone out of my head for the moment. The conjugate variables, that's right. The conjugate variable to distance is momentum. As the distance goes made smaller, the momentum gets bigger. As the time goes smaller, the energy gets bigger. So they go the other way around. So when you squash the remote, rarefied, very undense, very cold future, it gets warmer and it gets denser. When you stretch out the very hot, dense Big Bang, it gets colder and it gets more rarefied. Do they match? Not unreasonable. I began thinking about it. It's not unreasonable to think they match. They seem to match rather well, I thought. So is it well enough that it's possible to imagine that our Big Bang really is, in some real sense, the continuation of the remote future of a previous, real, in some sense, eon? I remember going lecturing all over the place to people, thinking, I can go on lecturing about this forever because nobody will ever be able to show I'm wrong. And then I thought, maybe they will be. I have thought, well, there is perhaps a way that can be shown to be wrong. In the following, well, I think it's my next picture. You see, the bottom of this picture, that horizontal curvy line is the join between the remote future of the previous eon to the next eon. And signals could be imagined to get through, as long as they're massless signals. Photons, you might imagine to get through. you have to worry about them because they get very scattered when they get on the other side. And so, well, maybe if they're a long enough wavelength, they might get through. It's possible. What about gravitational signals? Well, there's a good chance. You could think about that. What kind of gravitational signals could they get? What kind of signals could be strong enough that they might possibly get through and produce signals that we could see? Well, this was the idea I'd had. The horizontal plane going through the middle, you've got to think of that as a three-dimensional surface. That is the join between the previous eon. Our eon is the one above it. That's us right at the top looking back. That's our past cone, looking back to the stretched out Big Bang. What's the previous one? Well, that is a galactic cluster. In that galactic cluster, there is several supermassive black holes. From time to time, they run into each other, they swallow each other up, until ultimately there's just one left. Each time they run into each other, there is one walloping big explosion in the form of gravitational wave signals. An enormous amount of energy comes out in that form. Is that big enough that one might possibly see a signal on the other side? There's quite a long story here and a lot of opposition and people making fun of us and all that sort of thing. But finally, my Armenian colleague Wavy did look at an analysis where what he was doing was looking at triples. You see, when you look at several events, which might be, say, at least 3 events within the same galactic cluster, they would look like rings in the sky which are concentric. And his analysis was for looking at rings where the variation in the temperature around the ring was anomalously low. And to get a significant signal, he had to look at least 3 with the same center. So that was what he was looking for. And this is the sort of picture he found. I find this very remarkable. This is a picture where the points in here are triples of low variance rings. This is the Planck Data. So this is looking at there was what was it? The first one was the one I showed you before, and then there was the WMAP, and then there was the Planck Data. This was the most refined of the 3. And looking at the data there, he's looking at triples of rings. You plot the centers. The strip in the middle, you forget about, that's meant to be where the galaxy is, and so he didn't look there. But he looks at the top, at the bottom. What I find striking about this is not just the enormous non-homogeneity of the picture. Whatever it is that's producing these signals is very far from uniform, which goes against the current dogma of the cosmological principle, which says if you go to a big enough scale, the universe is very uniform. It doesn't seem to be so uniform. Whatever the reason behind these signals, it's not very uniform. Well, we claim that here we are looking at collisions between supermassive black holes. Another feature of this is that the color. What's the color? It's very confusing because red means cold. What I should say, red means hot, and it should mean cold, because blue is blue shifted, and that is warmer than red shifted. That goes the wrong way. The other thing that goes the wrong way is it's in the signals in the scheme that I'm talking about. The red shifted ones are the close ones, and the blue shifted ones are the distant ones, if I've got it right, and I always confuse myself when I'm saying it. But the upshot is that if this analysis is right, that the red ones in the lower right region are very, very distant. Outside what we would normally call our particle horizon, we shouldn't be able to see anything. It's before the Big Bang, you're seeing that. The ones at the top are, when I say before, I don't mean they're both before the Big Bang in the scheme. They're just within our particle. Don't worry about that. The blue ones at the top are relatively closer to us, I should say. And then there's sort of greenish one, which is in between. But what I mean is that there is this clumping in the coloring, which it was not selected for at all. So that where you see a clumping in the angular distribution, that's surprising enough. But for free, you're given this clumping in the color. If it's not what we think it is, we need an explanation. So now that was the stuff that we did. Independently of us was work done by a Polish group where they also looked for the signals that I was just showing you in a different way, and they also found clumping of the signals. We couldn't compare it with us very well because they were looking at different effects and all that. There is some comparison with the pictures that we found. But this, what I'm showing you now, is something else. This was looking at a completely different type of signal. This is looking at the eventual fate of black holes. What is the eventual fate of a black hole? Well, according to Hawking, we will get, here we have the Oppenheimer-Snyder sort of collapse, and now we also have the Hawking evaporation, radiation coming from the black hole as it. Well, how long is it going to take? It's an awful long time. So the sizable black holes we're supposed to be seeing, you have to wait for how many years? Well, something like 10 to the 100 years. So number of zeros, something like 1 followed by 100 zeros, number of years. According to Don Page, I think it's like 10 to the 103, something like that. It's an awful long time. That's relevant to what I want to say. But in that period of time, the black hole will finally disappear, but that energy isn't gone. It's there in the radiation. And what happens to it? Well, what happens to it is supposed to be in this picture. This is a picture from a paper written by Krzysztof Meissner, one of my Polish colleagues, Paweł Narowski, another Polish colleague, Daniel An, who is a Korean who now works in New York, and myself. And this paper was published about 1.5 years ago in the monthly notices of the Royal Astronomical Society. As far as I'm aware, I've never seen anybody comment on this paper. I've seen people comment on a sort of previous version of this paper, and we'd like to know. Now you see, what we're looking at, we claim, is Hawking points. Right at the bottom, look at the bottom horizontal line. That bottom horizontal line is meant to be the crossover from the previous eon to our eon. Right above that, the next horizontal line is 380,000 years later. One point at the bottom would have spread out to about 8 times the diameter of the full moon. So that's this kind of scale we're looking at. Now, what is a Hawking point? Well, you see this little world line at the bottom coming up and hitting that horizontal line at the bottom. That's meant to be the world line of a supermassive black hole. The evaporation due to the Hawking evaporation is tucked up right underneath that, within the blob you see at that point. It happens so late that it doesn't really make much difference in this picture whether it's there or not. But I'm still calling them Hawking points because in my view, it is in fact, you're looking at the Hawking radiation. But anyway, that's coming through, and in some form, it's just a burst of mass energy. That spreads out. You don't see anything for 380,000 years because the photons don't get out. They just scatter backwards and forwards. That's Jim Peebles' work and his company, and you follow that out, and then you see these spots in the sky. The analysis due to Christoph tells us, and the detailed work due to Daniel Ann looking at the figures, is that we seem to see, with a confidence level of 99.98% confidence, the existence of these spots. Where they actually are in the sky is not so clear. I think the best thing to do is to take Daniel's analysis, look at the 5 strongest points in the Planck data, because those are also seen in the W map in exactly the same places. You look at the next one in the W map, the 6th point, that's also seen in the Planck data in exactly the same point. I believe those 6 spots are real. Anyway, so I claim, and I also think, I don't know if this is true, but I think that if you were sitting in a planetarium and this planetarium was simply showing you the microwave background of the sky, that you'd see them. because the intensity over and above the general variations intensity is about 15 times as much as the normal temperature variation. And these would be spots in the sky. And I claim you would probably see these 6 spots. I don't know, it'd be very interesting to see. An experiment could be done with a planetarium. You see them with the naked eye. Well, not a naked eye, you've got this conversion of the... Anyway, thank you very much. That's...
Okay, so thank you, Roger. I need to digest that for some time. We've got some time now for Q&A. So we're going to be taking some questions online as well as in the audience. Omar, where's he gone? Okay, brilliant. Do you have a question ready for us?
Yes, we do have some questions coming in.
If you have a question in the audience, put your hand up now, and I'm going to send my PhD student to ask after this question. No, nobody in the audience has a question. Really? Come on.
There was a yes.
There was a yes. There we go. Okay, but we'll hear Omar's question first.
Right. One of the questions is, why wouldn't the early hot phase of the next eon disturb or destroy a signal coming from the previous eon?
I'm afraid my hearing isn't good enough. What was the question?
Why wouldn't the early hot phase of the next eon disturb or destroy a signal coming from the previous eon?
Well, it might to some degree. I mean, I'm looking for signals. In fact, both the effects I'm talking about. Let me just think for a minute. Well, the first one having to do with the gravitational waves coming from a collapse. There's mostly gravitational signals. So they pretty well come through the 380,000 years without being disturbed. So I think it's fair enough to say the gravitational signals, mainly because they're on such a big scale. I think it's quite possible that electromagnetic signals could come through if they're long enough wavelength. You see, it's an interesting question whether you could see magnetic fields coming through, because that's basically an overall. You're not looking at things like light, you see, which will be scattering backwards and forwards. You're looking at slight variations in the electric and magnetic field. But I think it's a real point, a serious point, what signals could get through and not be destroyed in those, well, right at crossover or within the next 380,000 years. So I imagine you would lose an awful lot in the way of signals. That's completely true.
Thank you.
Would subatomic particles like electrons survive from one eon to the next? Electrons, would they look the same thing if they survived?
It's a very good question because I didn't talk about that. You see, I've sort of pretended in my argument that the only things which survive in the remote future are photons, which is completely false, because there are things like hydrogen atoms. I forget what the main, there's certainly things like that which should be around. So what happens to them? Well, here is what has been said to me is the weakest part of the argument, which is perhaps why I didn't mention it. The weakest part of the argument is that I have to say that mass fades out in the remote future. Now, there is an argument which is not just waving of the hands completely, which is to say that when you do particle physics, almost the first thing you do, I don't really know because I never really did particle physics, but the first thing you do is you look at the Poincare group and you look for the Casimir operators of the Poincare group. You look for these things which are absolutely conserved, and they are mass and spin. So if you have a stable particle, its mass and its spin should remain constant. Now, when you have the sort of situation I'm talking about here with a cosmological constant, then I claim that the correct group you're looking at for the local physics is not the Poincare group, but the de Sitter group. And what are the Casimir operators for the de Sitter group? I'm not sure about spin, that may well be, I'm not sure about it. But the mass is not a Casimir operator. So this suggests that maybe there could be a decay of mass over a long period. Now this is, people say it's the weakest part of the argument. I'm prepared to admit that. But the general point is that over these enormous lengths of time, that mass will not remain constant. It will start to fade out, due to this fact that it's not Casimir operator. And that hydrogen will start to disperse, the proton and the electron will start to separate from each other, and then the mass will also fade out. And so you're left in the asymptotic limit, zero mass things. That's conjectural, and I agree with that. In the Big Bang, you also have massive particles, but there you have the energy being so great that you can say in the asymptotic limit, as you go back into the Big Bang, that the mass becomes irrelevant. That does depend to some degree on the particle physics, but there it's much more plausible, I think, that the mass becomes unimportant in the limit. But this is certainly a conjecture which would need to be true for this thing to work. So yes, it's not just photons. You certainly have electrons, but the argument would be they're mass-faded electrons, which in the limit, the mass would never be quite zero, but in the ultimate limit, the mass would be zero. So that's the argument I'm trying to put forward here.
Next question is, does time stop in a singularity?
I'm sorry?
Does time stop in a singularity?
Time stop? No. No, it doesn't stop. I know people tend to say, well, time stops with photons or something. I don't think that's the right view at all. Time races like mad. It's really the other way around. I don't know if that's what you mean. I mean, if you think of a massless particle, it doesn't experience the pattern. So, you know, the tick of time from its creation to wherever it gets to is zero. So in other words, time is racing past at an enormous speed. So it doesn't stop. I don't know if that was the sort of point that you're making here.
We had another question.
Yes.
In the hall.
So do you think that there's a possibility that we won't find a quantum theory of gravity, or if we do, it won't be anything like what we expect it to look like? And if so, what does that mean for reconciling physics with relativity, or quantum mechanics with relativity?
Latter. Perhaps saying it won't be anything like, I wouldn't say that's, I think it's got to be a lot like it. It probably will be as like quantum mechanics as Einstein's theory is like Newtonian theory. So put it like that. There will be an aspect to it. You're looking at quantum mechanics from a different angle, and it will look quite different. So we see when you look at gravitation theory from the perspective of general relativity, gravity is not a force anymore, which is a huge change from the Newtonian way of thinking of it. But on the other hand, it doesn't make that much difference. And certainly most of the physics you're doing, you get away with using Newtonian gravity, and it works wonderfully. So in the same way, I would say that the modification that is needed for quantum mechanics will be conceptually as big a leap as going from Newtonian theory to Einstein. Yes, there I think is big a leap. But as to the details of what you get in the predictions of the theory, most of it won't be affected. So the way that quantum theory works, most of the wonderful things it does for us now will carry through just as before. So that's I'm only speculating because I don't have the theory, so who knows. But my guess is that the framework of the theory that we end up with will look as different from current quantum mechanics as Einstein's general relativity looks from current, from Newtonian theory.
Are the future boundaries of black holes necessarily complicated and not spherical?
What was it with black holes?
Are the future boundaries of black holes necessarily complicated and not spherical?
Well, the singularity, I don't think there's any reason to believe that the horizon will look anything other than pretty spherical symmetrical, because everything pretty well, I mean, even the rotation will gradually get lost. And so you expect it to end up asymptotically as a Schwarzschild solution. But that doesn't apply to the neighborhood of the singularity. If you go in towards the singularity, you will get all hell breaks loose. I mean, I would imagine, and I have no good reason to believe this, but I would imagine that the analysis done by the Russian school, as corrected by Belinsky, could well be appropriate. I mean, they have this extremely complicated picture, and Charlie Misner in Princeton had a similar picture from a completely different perspective. It may not be right, I don't have good reason really to believe that's right, or how general it is, but it could well be extraordinarily complicated. So nothing like what you get in the Schwarzschild solution.
Oh, so there's another one up there.
Is there a limit as to how many eons could exist or could have already existed?
Well, there's a good question, isn't it? Some people try to toy with the idea of there's only one and we just go around in a loop. I don't much like that, because you have this consistency conditions in the matching one end to the other, which I think is a huge constraint, which I think is pretty hard to. Maybe there are 17 of them, you know, like the cicadas or whatever it is, that hibernate for 17 years. I just say the simplest point of view is it's infinite. I remember visiting the Vatican at one time and putting this to them and wondering how the picture of creation was modified by this. What was I was really quite impressed by how prepared to take it on they were. Yes. But you see, I would argue that the simplest picture is an infinite number of cycles. And therefore, that's what I would put forward. But if somebody says, no, there is a gradual trend and some parameters change and change and change, and it gets less and less, there is certain very small amount of evidence that it doesn't change all that much from our previous eon to us. And if somebody asks me a question about that, I'll talk about it. But
So this is currently the last question coming from our remote audience. What is the wavy section at the edge of the universe cone?
the what from the edge of the universe?
What is the wavy section at the edge of the universe cone? I think the question is referring to the pictures you showed.
At the edge of the universe. I didn't remember the edge of the universe. You mean the Escher picture, do you think?
No, it was the light cone. It was all corrugated. I think that's what they meant.
The light, yeah, I'm a little bit confused. You have I mean, you see, I'm not arguing that spatially there is an edge in that sense. I don't know if that's what you mean. I mean, we don't know whether it's closed up or whether it keeps on going indefinitely. That's up for grabs at the moment. So there's no edge in my picture in that sense. The edge, if you like, is where your past cone hits the Big Bang surface, but then I'm saying that isn't the edge, it keeps on going. So a past light cone just goes right through into the previous eon, and then it might go through into the eon before that. So you might even receive signals from 2 eons back. I don't know if that's an answer to your question, but...
Where's my student gone with the microphone? Okay, great. So this chap had a question.
Does the current observability of the universe pose any limitation on what can actually be said with regards to, I don't know, you suggested that maybe the singularity doesn't necessarily have to be kind of this perfect thing. So
singularities in the future or the past?
from the past, like our current understanding
I
of.
mean, see, my argument is that the singular in the past is not singular. It's not conformally singular. That's the key point. You see, we think of the Big Bang as being singularity, and certainly the early part of my talk was talking about that, and that was, sure, people, including me, we used to think of that as part of the same story as the singularities in the future. But what I'm arguing for now is it's a different story. The singularity in past is a singularity in the metric, but not in the conformal structure. So the conformal structure is smooth and it keeps on going. So it's not singular. You have to describe it in a way that the actual metric is not the important thing to talk about anymore. You talk about conformally invariant structures and so on. The singularities in the future, that's another story. And sure, they just wreck the space-time completely, get crunched out of existence. But they get squashed into the Hawking points. And so what happens on the other side, we don't know. But as far as the arguments in my discussion go, it doesn't matter, because all we're seeing is a source of energy which spreads out, and then you see a spot in the sky. Maybe someday we will need to know what the structure of that is, and maybe there will be enough detailed information that that's important to know, and then new theories will be needed to understand what's going on there. But that's certainly beyond anything I'm saying here.
Okay, so we have another question from Max, I believe.
Do the so in the previous slide with the locations of the collisions of supermassive black holes, do the ones indicated by blue, do they correspond to the locations of galaxy clusters or superclusters?
There's an extremely interesting question here, which I've only become acquainted with recently. Some people have been looking at quasars and the concentrations of quasars. And as I've recently learnt, you have not only sort of big clumpings, but you have one particularly enormous clumping of quasars. These are in our eon, so you're looking at quasars, I guess very distant early quasars. And apparently, so I asked this fellow, where is this biggest, huge quasar clumping? And I was told where this is. And I thought it looked remarkably. You see, what I would like to have seen is it's right in the middle of this blue region at the top. That would have been, there's an explanation. There's that huge concentration of supermassive black holes and maybe Hawking points. It's not there. It's just on the edge. So I'm left not knowing what to make of it. But I think it's a really interesting question. Can you look at these? Well, what am I saying there? Yes, those are looking at the collisions between supermassive black holes. That's not the Hawking points. You're looking at the collisions with supermassive black holes, and is there any correspondence with clumping of quasars in our eon? Because you might imagine that as the black holes, if you've got lots and lots of black holes, then there'll be lots of Hawking points. When I say Hawking points now, I don't mean the ones we see, because ones we see are right on the edge where our past outcome hits it. But these are ones in the middle, which we don't directly see, but they could produce effects of maybe new supermassive black hole clumpings or something, I've no idea. But it would be very interesting to study what the impact of these things would be. Yeah.
Okay, I mean, we could ask Roger questions till the end of time and we enter a new eon. I don't really want to do that. So we'll have two more questions and then we'll finish off. So.
How much freedom is there for things to change from eon to eon? In that if the history of the universe is deterministic, does that mean that the same things have to happen between eons?
Oh, I see. How much freedom? I don't really know. I mean, I think there is a fair amount of freedom. Certainly, I'm trying to say that it's not as uniform. I mean, that seems to be evidence from Vahir's pictures, that the universe on a huge scale does not seem to be as uniform as people on the whole seem to believe. What's called the Cosmological Principle, which seems to argue for uniformity. Now, does that mean the eons aren't all that like each other? Goodness knows. I mean, there are nice speculations one can make here. There is a little bit of evidence that the previous eon to ours was not too different from ours. Now, what do I mean by not too different? Well, you see, you can look at how big are the rings that you get, which we claim are from collisions between supermassive black holes. And there was a calculation done partly by Paul Todd and partly by some people at the Perimeter Institute, I think it was. And that was to look at how early do you expect to see these collisions take place? And that means how big could these rings get? And the conclusion was that if the previous eon was like ours, they couldn't be bigger than about 40 degrees across the sky. How big do we see them? About 30 degrees across the sky. That's pretty consistent. So that seems to indicate that the previous eon wasn't that unlike ours. It's a pretty feeble, we'd need a lot more evidence than that. But it looks as though it was not that different from us.
Okay, the last question, I'm sorry to those who've got their hands up, we are running out of time. It's the chap in the centre.
Thank you. Just building on that point about the potential difference between eons, assuming we still have to have some explanation for the fine-tuning in the universe, and as I understood it, you were not over enamored with the multiverse approach, then how do we explain that there isn't substantial transition between eons in order to explain that we happen to live in the one of, trillions that is able to support life and have all those issues without either the multiverse or substantial transition between eons?
Well, you raise an important question here, and I can only answer it with my own prejudices, I think. You see, I'm not convinced that the fine-tuning... See, I think we know so little about what, if you were allowed to change the constants of nature, what would happen. I don't really know. I mean, who knows?
Neither do I.
I don't think anybody knows. What really would be like a universe in which you're allowed to change these parameters? Are you allowed to change these parameters? Is there some overriding theory which tells you, for some deep reason, that these numbers have to be what we find? I don't know. I think it's a deep question, and my view, we're really very far from having an answer to that. It's a bit related to the previous question. I mean, I know John Wheeler liked to have this idea, and I think he was rather like to play with the old Friedman model, where you had a spatially closed model, and then it did that, you see. And then there was Tolman's version when it changed, it didn't quite repeat itself, and so on. And Wheeler liked to consider, well, each time it bounced, there was a churning up of fundamental constants, and they came up with a different set of values. And then we happened to find ourselves in the lucky one, which is just there, where these numbers came out right and were suitable for life and all that stuff. I don't think we know enough about what creates life, what it is that determines these numbers, what interrelations between them there are and maybe have to be for some deep physical reason. We're probing around in the dark here. And so how much fine-tuning there really is, I mean, I like to think of science fiction stories. One of the ones I really liked was one of these ones where, what was it? There was a neutron star coming to visit us, and there was a life on the neutron star, wasn't it? Yes. And they went through an their time scales was sped up by an enormous factor from our time scales. And so they went through a huge evolution in the time, in a year, you see. Oh, it was a lovely story. But it just showed probing the possibility of changing these numbers. That's great fun. How much of it is science? I don't know. I think there's a lot to be talked about, and we can probably talk about these things endlessly.
But let's not. So please, everyone, thank Roger again for a wonderful talk. It doesn't quite match the Nobel Prize, but we have this fabulous artist that we get to do these wonderful pictures of our, you can see it, no one else can, of our Stag lecturers called Oliver Dean, who works in Bath, and he works with researchers and educators. And he's done this wonderful picture that Roger can take with him. So this is for you. So you don't have to carry it.
Well, thank you very much.
The Penrose tiles in the background, not everyone can see that.
I did.
You recognise it.
I sort of recognise it.
So just before we finish, it's really important to thank everyone who's made this happen today. So the staff at Turner Sims, the FOSS team, iSolutions, and especially Barbara Saiter, who couldn't be with us today, but spent a lot of time working on this, and I hope is joining us remotely. So I'd like to put our hands together to thank them, please. And I should also thank my wonderful committee members, but they're all right. They can manage without the applause. Just before we say a final thank you to Roger, just be careful on your way out. Give everyone lots of space, and please be careful. Those of you who've got tickets across in Building 56, we'll see you there shortly. So for one last time, let's thank Roger for a wonderful event.